Hi YouTube. I was going through the Klipper implementation of Input Shaper because I wanted to make a small video series about, first of all, how to use it, how to interpret the graphs, and of course also how it's actually implemented and the different algorithms used. So I was doing the reverse engineering, and I think I found a bug, specifically in the part where the resonance frequencies are measured. Actually, it seems to display a wrong frequency compared to what it's actually measuring. It kind of balances out later how Input Shaper is implemented, so it doesn't destroy functionality, but the graphs are basically wrong or shifted in frequency. And it's shifted by 1 over the square root of 2. The actual frequency you're measuring is 0.7 times lower than the frequency which is shown. So let's dig right into the implementation, and I will show you how it's implemented and how to interpret these lines of code, how it's interacting with the kinematic model of Klipper. And please also excuse the bad video quality. I only have my webcam at hand right now, and I don't want this video to be taking a lot of time, so I didn't get the camera equipment. So let's have a look at the code and what I think is wrong here in the mathematical or physical assumptions. So at first, what does the measurement do when we're trying to measure the frequencies, the frequency response? We are shaking the printhead at a specific frequency, and then we're measuring accelerations. And from that, we try to conclude how it reacts to those frequencies and to which it reacts the most, and where we need to dampen them, or better, it's not really dampening, it's just like trying to avoid them during the movement actually. So let's start with the printhead. So this is my printhead, and we're going to move along the x-axis, and then we're starting the movement from here and going to move back in the specific frequency. So looking at the frequency, this means the time when it goes here. This point in time would be this point, and that point here is here. The period time of any frequency is t is 1 by f, right? So this is 1 by f, this is 1 by f half. So if we try to stimulate the printhead at a frequency we're measuring, this movement has to be in the length of time of 1 by 2f. So a half of the time we need for the full frequency period of the resonance. Okay, let's keep that in mind, because that's of course important. So how does Input Shaper implement that? So we are going to look, first thing to notice, something I missed at the beginning, is that we set the maximum deceleration to the maximum accelerations, this value here, so deceleration. Which means we're going to set lower accelerations later, that the acceleration, deceleration are always the same value and always the value we're going to set later. We also, or Input Shaper does something during going through the frequencies. It starts at a lower frequency and then steps up to the highest frequency we want to measure. It also increases the acceleration during that. And for that, we have the maximum acceleration and define something, I call it AF times F max, and this is later here called self-accel per hertz. So self is just the object, so it's acceleration per hertz, but I would call it acceleration per frequency actually. And yeah, that's what we are looking at. That's something to keep in mind for later as well. So now we are here in our jumping into this while loop. This while loop is basically just there to iterate through the frequencies, and whenever we go through the frequencies, it measures or tries to move in that within that frequency, stimulate the printhead, and then it measures the response and gets to the next frequency. Okay, and we can see we create a little offset here, which is probably to avoid being able to divide by 0 or multiply by 0 here, because both cases would be critical. Of course, a division by 0 would cause the program to kill itself. Yes, okay, so then we have something which is probably the time for the segment, T segment. I'm going to call it in the same way now. I'm going to call it TS, and that one is 1/4f. And we can see this is basically half of the time we need for a one-directional movement. Okay. Then we define something which is called maximum velocity. That's the velocity we're going to request from the kinematic system of Klipper when we are doing the movement. And we know that we are constant accelerating or deaccelerating for movements, and that's the target. And that maximum velocity is defined by A times TS. And A, of course, I forgot to write that down. A is our AF we defined over here, this AF, times the frequency we are going to measure. And that's the first thing, which is, yeah, it's not a mistake in the implementation, but it's not really nicely done. This value is constant for it's only dependent on Fmax and Amax, and those values are constant within the measurement, and we recalculated every movement, for every new frequency. It should be out of this loop, so this should be somewhere above. And we can show that easily because A is AF times F divided by 4F times TS, and that's AF fourth, and AF is, we can see that here, that AF is A max divided by F max. So it's just the maximum acceleration divided by 4 times the maximum frequency. So that's how you should calculate it. Okay, so now we have the acceleration and a maximum velocity for a movement calculated, and then we set the velocity, the acceleration in the printhead. This is just setting the limits, and that's the acceleration we are going to have for the movement. Now, for the length of the movement, we calculate the L, and L is a half time the acceleration times TS squared. So we had this segment time, and then that's just how long the distance it takes to reach the maximum velocity we defined here and it's also the length is also the time of 1/4s if we're constantly accelerating. So looking at this, we're going to move from, let's call this point A, this point B, it can be on any axis. So we move from A to B. This distance is L, and if we're going to look at time, we're at the point A, we're at point B at that 2 times, this is the velocity, and if we would constantly accelerate, that would reach V max here after the time TS. That delta T is TS. So, of course, this is not how movement happens, because our kinematic system does not only accelerate, it also deaccelerates. So how does that one look then? And to reach the time, we also know that the time we need is 1/2f, not 1/4f. And I think that's where the mistake was made. I think whoever implemented that thought that he just is reaching half the speed on the way, so he takes double the time, but that's not true. So how would it actually look? We have, again, time and velocity. That's, yeah, okay, we can, S from 0 is A, S from TS is B, and then we're constantly accelerating, but we don't reach Vmax, because Vmax would be reached at the point B over here. And then at half the point, after half the distance or half the time, we are deaccelerating. So this is symmetrical around this axis. And this here is actually V max half. So this is not the same as here, of course. Now the question we have to ask, what is TS? And is TS just 1 over 2f? Because that's what we need. And that's not the case. So how can we calculate that easily? We have L is 1/2 over ATS. Then we solve that squared, of course. We solve that for TS, which is square root of 2 times square root of L divided by A. So we're going to have a look at L. So we're doing that whole thing like that, better, times square root of L. That's T in more T. Yeah, right. What we are going to do is calculating the time we need from here to here. Okay, I should have mentioned that probably. This is the area that we're calculating this time, TP. And TP we know is reached when L is half of the length. So TP is times L half. And that's nothing else than our original TS, which is 1 over 4f times 1 divided by square root of 2. So now this is only for half the travel, so we need to double that. And let's call that TT, T target. Therefore, T target is TS times, yeah, I write it down like that, which is TS square root 2. Yes, and that would be, so to go ahead, I'll remove some parts just to be able to write. So we've taken that one, TS, no, TT, we call it TT, sorry. No, TS here, of course. TT is TS times square root of 2 is 2 over, no, square root of 2 over 4f. And of course we could now make that a little bit simpler. It's 1 over 2 square root 2f. And we can see it's not 1 over 2f what it should be. So what it basically means, we are measuring the wrong frequency. We are stimulating in the wrong frequency, another frequency than we expect to do. And I just realized I forgot to push the button for audio recording, so you will only get the audio recording of my tablet. I hope it's not too bad with me touching the screen all the time. So what we can conclude basically at the end is 1 over 2f times 1 over square root 2 is not equal to 1 over 2f. So what this basically means in the end is that every frequency which is shown during measurement and in the input shaper graphs is shifted by this factor 1 over square root of 2, which is about 0.7. So the frequency shown is too high, or the actual frequency is 0.7 times the shown frequency, so it's lower. And I know this is kind of a strange way to form a bug report, but as it is a combination of the kinematic model and the code shown, I thought this is probably easier than doing a write-up of that, especially for me probably, to be perfectly honest. And then I also thought it might be interesting to just see how this is working for others. Might be interesting as well, despite the bug, and maybe also gives a glimpse of how debugging those things works, or reverse engineering. So you need to understand the kinematic model behind what it does, and then you look at the code and try to understand what is it doing at this specific point and how does it handle this. And of course I only show a few lines of code. I think it's like 30 lines or something like that. But to understand what I did now, you have to look at way more code, of course, and understand where you start, what does it do. And for example, the toolhead.move is of course the function which controls the movement, and I had to read through that as well to understand if the deceleration is actually considered as I would expect it to be. And it's also quite interesting because what happens at the peak when the acceleration turns around, because then you have that small point, that infinitely small moment of time where the acceleration is actually 2 times the acceleration you would expect, because you're going from plus to minus, so the force at this very moment is twice the force you would expect. And a lot to consider there and to look into. I hope it was not too long today, and I wish you a good time.